Good morning, everybody. I'm on the West Coast at our annual hand meeting, which concludes later on today. And these are folks presenting today. Everyone we know, colleagues, similar, and we have some of the principals and investigators here, funded by NIH, state, the Department of Defense, and this is really an opportunity for physicians, therapists, researchers, students, institutions to collaborate. And this is a photograph of a patient with an international classification group 1. The traditional surgical procedures in a single stage include a single transfer with the only necessarily good remaining donor muscle, the brachioradialis, to reanimate wrist extension, followed up by tenodecies of the EPL, FPL, and a portion of the FDP. And this is that sort of level targeted by neuromuscular stimulation, or FES. And I'm going to just hopefully play this video here. And this is individual with a tendon transfer trying to comb her hair without any stimulation. You can see the tendon transfer is performed over there on the left, the voluntary control that she has at this point. This is after an earlier generation FES. And it takes a bit of a minute, but you can see that she's had much more control there. She almost dropped it there. Reactivate, open, change of grasp. And she has bilateral systems, as you'll see here in a minute. And this is a incredibly collaborative group of surgeons, researchers, programmers, students, as I said before. Initial validated outcomes in the mid to late 2014, 2018. These are the two grasp patterns initially programmed: lateral or a key pinch grasp, and then palmar grasp. The requirements are pretty important. Obviously, the spinal cord injury lesion renders a group of muscles paralyzed, as you can see on the bottom right. You still need to have some cortical control over a muscle which coordinates the system. The good news is that those muscles that are distal to the lesion, which are paralyzed, they still remain electrically active. And I think Dr. Kirsch mentioned some of this, and the premise is still the same. It's just that the control is different between the two types of implants, but the basis is still the same. And the important thing to think about here is that even though the lesion is, let's say, a singular level of C5, C6, it actually has a bit of spread. And in this transition area, there's voluntary muscles above the lesion. There's some very, very difficult muscles that present a problem, which are lower motor neurons, or denervated muscles. And then the upper motor neurons, as Ron will talk about as well, are still electrically active. The reason I paused here for a second, because it looks like the Zoom's trying to do something funny. If you can still hear me, I'm going to continue. So there are methods to determine which muscles are electrically excited and paralyzed and not denervated. The reason I really focus on this is that despite any technology, a denervated muscle represents a big problem for us. So the initial control of the myoprosthetic, some of the stimulating electrodes have changed to a certain extent, but the basis has been really maintained over the course of several decades now. And what you can see here is as we've added this MES electrode, and I think Ron will talk about this. This helps control the system and give feedback to the system, so it becomes a little bit more transparent. And here we are, 2016. Now we'll discuss what's happened over the last 5 years, albeit a little bit of a pause over the last 2 years, to go from external control to some internal myoelectric control, which still requires a box, to everything that's pretty much completely inside. And this is the full implantability based on some patient feedback. As you can see, the stimulating electrodes and a stimulator have been implanted since the beginning. And as you follow this chart down from left to right, top to bottom, the control sensor power and processing go from external to internal. And this is based on both the user as well as technology improving. So here's a second generation implant with a epimasial electrode. This is still sort of the concept technology workhorse. This is a individual with a bilateral system, and you can see it gets a little bit busy in the subcutaneous tissue as well as in the chest area. But it's really internal control by intact muscles. And in most of our patients, it's either the ECRL or brachioradialis in the forearm. We have utilized the muscles above that in the head and neck, auricularis, platysma, trapezius, as well as sternocleidomastoid. So, as we get above the spinal lesion, we're still using some voluntary muscle control, not cortical, as you saw in the last talk, but certainly something that's connected to the primary motor cortex. So next generation is high tetraplegia, internal control, different electrodes, and combined upper and lower extremity systems. I'm going to re-emphasize the denervation effect again. I can't do it enough because Anne showed 2002 that if the tricep is denervated in this lower motor neuron, there's really a elbow contracture, and that represents a big limitation of functional workspace, at least for the upper extremity. We do have some tactics and strategies to improve the denervation, and this would be muscle transfers. And we've actually performed several paralyzed muscle transfers, which is quite interesting. Is that it's best maybe to perform a voluntary muscle motor nerve transfer, but in instances where there's very few motor donor nerves, we've been able to use paralyzed nerves to denervate a muscle for later FES or a neuromuscular control. Nerve cuffs, which we've seen, and I think Ronald mentioned something about the spiral nerve cuff, the fine. In addition to the spiral nerve cuff, most of the upper extremity is done with epimasial or intramuscular electrodes, but the plan is later to also use nerve cuffs. And this is sort of the combined system, and it gets even a little bit busier with implants in the chest as well as the abdomen. But it's certainly possible. This is a bit of an old video in someone with high tetraplegia with very little voluntary motor units to, with a nerve cuff, stimulate, for instance, the whole radial nerve. I think that's Bob Kirsten in the background. So third generation network neuroprosthetic, and I'll wrap up with this in a little bit, is that it's now utilizing these different electrodes, albeit, as you can see up in the top, the nerve cuff isn't part of this plan, but certainly part of the next several plans. And there's a main power module, but then remote modules that connect with a single cable instead of all the other cables which you've seen. The electrode type is very similar, but as evidenced here, the number of electrodes can go much higher, from 8, then to 10 to 12, and now finally to 16 is possible. And it allows us to target the finger intrinsics and, as we'll hear in the next talk, the trunk. And the progression of control also has improved. So early surgical intervention is important. Multi-channel implantable units, nerve cuffs, control feedback in the hand position, and EMG. And it's a conversion in a schematic from the implant, for example, on the right to one on the left with a main power source, and then individual connector modules. On a schematic, this is what it would look like. This is actually one of the diagrams from one of the patients. And as you target this, the lower right abdomen, different connector modules, remote modules in the right upper chest, right flank, lower left abdomen, and then left flank. And these were then from the operation or clinical photographs at the time of the operation. This is, sort of for the more intense computer people and tech on the power module. There's actually been some upgrades on the port plugs and the electrodes themselves, as we've had some technical issues over the last several years and getting everything to work appropriately. We have 5 patients in the present study with a plan to do at least 20. Stimulator module, or the remote connector module is what I call it. And there's a sensing module. We talked about this to a certain extent. This is the entire system is driven by feedback from some intact voluntary muscle in either the upper extremity, head, or neck. Again, this is a more detailed schematic and eventually plans for the trunk and lower extremity. First human implant was January 2016. Let's see if this video plays. I'm going to pick one with good videos, I'm sorry. This shows sort of the importance of reach. I put this slide in here, and this is a segue into Ron's talk on how important trunk and mobility are. This is our own Kim Anderson, primary researcher, principal investigator, and participant, demonstrating that with wonderful feedback and control, this combination of key pinch and lateral grasping and popcorn. The trunk is of big importance, and I'm going to stop here because I don't want to necessarily steal Ron's thunder for trunk control priority for quadriplegics as paraplegic. So that gives you a little bit of a brief update. Where we are now is changing one of the port plugs for reliability. We've had some connection issues between the network and the remote or stimulating modules. And that's being worked out over the next, let's say 6 months, although we always say 6 months, and hopefully reimplantation with some revision for some patients and the new patients in 2022. Okay, thank you very much. Stop my share here.
For Dr. Hoyen.
Yes.
Any questions for Dr. Hoyen? How many patients have you done now?
We have 5 in the study right now. One patient had an infection in explant, so 4 active. Well, they're all 5 active, but 4 active stimulators at this point.